We're so very pleased to be with you, and we'll be looking at some stellar data, variable star data, and some binary star data, possibly as well. Now, um, J.D. Armstrong has been one of our stellar science hosts, and he is here in Hawaii. I'm on the Big Island in Hilo, and J.D. is on Maui. Now, he is the project scientist at the Faulkes Telescope North and is the Maui Technology Education and Outreach Specialist. So, without further ado, let's go ahead and get started. JD, welcome and thank you for being here with us at the end of your very long week.
All right. Well, thank you. You might hear in my voice that I'm just getting over a little bit of a cold. So, but great to be here. Good to see you all again. And like Jamika said, if you have any questions, if I start getting confusing on anything, please don't hesitate to ask. This really is your time, and I just want to help you understand. And let's see here. I think that we talked about, now, am I correct that you're using observations from Los Cumbres observatories? Is that correct?
Yes.
Okay, good. Okay, so and the reason I wanted to know that is I'm going to kind of skip over the process of flat fielding, dark correction, bias subtraction, because Los Cumbres will do that for you, which is just makes life so much easier. And so at that point, I think what we probably want to do is once you have your observations, the next thing that you're going to want to do is measure the brightness of the target that you're observing, right? And so there's a my understanding is that you're looking at binary stars like transiting binaries or something like that.
And I think they are going to use software.
Pardon?
For the
Sorry, we didn't quite catch that. You can also put it in the chat if you'd like.
Yeah, if that would be easier. I'll kind of go ahead, but yeah, and always let me know what you're working on. That way, I can kind of help with things. Oh, I don't want to be opening VStar. That'll be later. The first project or first program I think I want to show you is AstroImage J. So you can get AstroImage J free online, which is part of the reason I like it, is that it's free and you can get it here. And so let me send that link to everyone. I think, Jamika, you've already got that link.
Yeah, I did send it to Karubo already, but it
Okay.
doesn't hurt. I'll go ahead and put it in the chat again. Yeah.
Already got it. Okay, good. All right, so AstroImage J. So what the idea of photometry is, we're trying to measure how bright the star is or the target. And what we have is we have sort of we have a CCD that has a whole bunch of photodetectors, little photometers. And the light from the star is kind of spread all over over multiple pixels. And so what we do is we just draw a circle around the pixels, and we add up all the values from all the pixels. Is if you double the light for a pixel, you should get about double the response. And so they're linear. So basically what we're going to do is we're going to just add up all the pixels inside of a circle, and we'll worry about how large to make that circle in a moment. But then there's also light from the sky, and so we want to estimate that. And so we draw two more circles. And yes, you may laugh at my artistic skills. I will not be offended. But we draw two more circles out here, and we sort of use this to get an estimate of how bright the sky is in each pixel, so that then we can subtract that off from our target, so that we just get the light from the target, not the light of the target plus the sky. All right. And so the program that is really great for doing that on multiple images is called Astronomer J.D. This is something I've been using. I don't know if I should say this, but I actually was using it in a paper that we just submitted for publication on a Dipper star. So this is a star that has something transiting it, and the transit was like 90 days. It was ridiculous. So once you open Astronomer J, this is all that opens up. And if you're trying to make a light curve, which is what we'll do, you want to go into File, Import, Image Sequence. Okay. And then you can browse on your computer to go to the target that you want to reduce. And all the images are in this folder. And so I open this folder, and this is one of the first kind of quirks of this program. It doesn't show any files in the folder. But if I go up there and go and navigate on to that same folder using just a window, okay, you can see there's actually 55 images in here. It doesn't show them. And so that's kind of weird. But once you get used to it, then you just select this folder, and then it says, okay, you've got 55 images here. We'll start with image 1 and we'll go up to image 55. Okay, that's great. So it's one of the quirks of the program. There's one or two of these little weird quirks that I'll alert you to. But overall, it's a pretty nifty program. Once we selected the folder, just go ahead and click on OK.
So JD, if they have their own stellar data, they would need to already have that in one particular file, so that when they import it into Astronomer J, it's just the one file, and it can read all the images there.
Yes, you want all your images in one folder, so that the program will open up all the FITS images, or in this case, FITS-zip images that are in that folder. And so you want to put all the images you're working on at one time, all the images you want to work on together in one folder. Now, sometimes on older computers, or with sometimes the installation just does this, there are sometimes limitations on how many files you can open up. So you may have to break it into smaller groups. And also when we do photometry of asteroids, sometimes we want to break it into groups for other reasons. And so it's okay to go ahead and break it into groups if you want. In fact, it's not a bad idea. And then, so the next thing is you want to make sure that your target that you know which one's your target. So I'm going to just go to Simbad. I would imagine that you will know which one's your target, but I don't remember on this one. Usually I put it in the middle, but sometimes I do otherwise so that I can get some good stars for comparison. So I'm just going to go to Simbad and we'll go ahead and search for that. So this is WASP 163. This is an exoplanet transit, so an extrinsic variable star, if you can go for that. And okay, so let's see here. I thought I was able to do this last night. Okay, we're trying to match the stars in this field of view and the stars in this field of view. Okay, so that, something like that. Okay, well, the next thing I can do, it's going to be difficult. So I'm going to open this up in SAO image DS9. This is another way of doing this. I'm going to just open it in DS9. I'm going to hit scale, which scales the brightness on the screen. I'm just going to select 99%. I found that that's a good scaling to make all the stars visible. Then I can right click and drag if I want to sort of fine tune it. I'm going to go to edit, region, and oh, there's the match. Okay, so this star, this star, this star, this star, this star, this star. Here's that, here's that. But then again, that's not what we need to match, is it? Okay, sorry. Carrying on. Make sure north is up, east is to the left on this. So I'm going to edit, region, and then when I click on here, I can put a circle. Double click on the circle. And this is not the right target. That's the problem. Let's see which. $163. Okay. Well, this is a little embarrassing. I apologize. Apparently, I have the wrong target. So let's do this. Let's figure out what target I do have. So I'm going to use Simbad again. Just going to go ahead and paste the coordinates in here.
And the coordinates here are the right ascension and declination.
That's correct. Yes, yes. Okay. I apologize. I did try this last night. Okay. Okay, so this is this one right here. And so that's the target. And then if we try to match that, that's a much better match. So we have these two stars here. We have these three stars here. We have the target here. And these, okay. Well, we'll see if I'm doing a different target than I was last night. Okay, so I'm going to go ahead. And now we need to set up the aperture photometry. So the first thing you want to do is you want to determine how big those three circles are. And so I'm going to click on an isolated star. In this case, the target is a good one. Just going to click on that. And this is another place where Astronomer J is a little weird because it doesn't do anything. But it registers the click. It knows that I clicked there. So I can go into Analyze, Plot Seeing Profile. And now it shows me that I've clicked there. So it's just a little weird. But it comes up with a recommended radius for the source and the background, the sky. I'm going to go ahead and accept those apertures because that looks like a pretty good, some pretty good choices. Okay, once I save those apertures, I can close this window. Then I want to clear off this marking here so I come up to the broom and sweep all the apertures off.
Now, JD, for those who may not be aware of what aperture is, could you quickly explain that?
Oh, apertures are the circles that we were talking about. So this would be a set of apertures. Okay, the circle radii. And you don't always have to do circles. You can do ellipses or other shapes, but usually we do circles. Leave the fancy shapes for advanced work. We'll do that in a later session when you're about ready to start teaching me. All right. So the circles are good for most cases, but maybe there's something that kind of blocks and you want to avoid it. Okay, so we swept off, we set the size of the apertures, the size of the circles. And so now what we want to do is perform multi-aperture photometry. Okay, this window will show up. I'm going to screen capture this window because there are a lot of settings here, and you're going to want to have something like this to see what settings I use. And once you've used it a few times, then you will go with your own settings. Okay. So the first setting I have is fixed apertures as selected above. In other words, use these radii that we determined from that first image. Okay. You can also do, you tell it, oh, just go ahead and figure out what the apertures are from the first image or from each image. There are other choices there. For beginners, just go with this. And then if you need something better than what you're getting, then maybe try something different. We're going to place all new apertures this time, which means we're going to put a new aperture. We're not going to use what I used last night. Okay. We're going to place first, and then the other options are you can use what was used last time you used this program, or first previously used aperture, and then it'll figure out the rest. Okay. When going from image to image, you can use right ascension and declination to locate the position in the next image and the third image, or you can, if you unclick this, it'll use just the coordinates of the pixels. So wherever the pixel is centered, sometimes that's better. Usually, if you're using stars and you have a good reduction like most Goomba usually does, you can just go ahead and click that. If your target is a moving object, you can click this. You don't know how happy I was to find that when I was trying to do some asteroid work, because asteroids tend to move. You can also do single step mode if you have a particularly challenging set. Sometimes you want to do this, which basically each image, you'll click on the first target and then it'll try to select the rest of the targets. And then you can move them around, tell it you're done with the image, and then go to the next one. Hopefully you won't have to use that too often because it's a little painful. It's a little unpleasant to do. You can tell it to choose comparison stars that it thinks would be good, and it'll go to a catalog and look for comparison stars and show up with those. You can also enable the log. I don't know what that does, so I leave it alone. Auto thresholds, again, that's something I don't tend to change, and so I leave that alone. Centroid apertures means once it's found the target in the new image, then it'll let it move around a little bit to get perfectly centered on the target. Usually you want to do that. Usually, I think it comes with halt processing on world coordinate system or centroid error. So, in other words, what this says is if you have a problem with one of the images, just stop. I don't do that because there are too many times where there's a problem with one image and that it stops, 5 images in and I, have to start over. So I usually leave that off. And if there's a bad image, then I go back. But that's because I get excited. I want to see my light curve. Um, Remove stars from background. Okay, if you can do that, go for it. Assume background is a plane. I don't have that clicked. You might want to try that. The next one that is important is prompt to enter reference star apparent magnitude. If you want to measure the apparent magnitudes, how bright these stars actually appear on a meaningful scale, then you need to tell it how bright something else is in the images in order for it to calibrate them. Okay. And then update plot while running. Well, yeah, because it's more entertaining. And show help panel during aperture selection. Probably a good thing to have. Update image display while running. Yeah, that's kind of, entertainment value while we're waiting for things to happen. Okay. So we're going to go ahead and place apertures. Here's our help window that we said we wanted. So it says left click, add the target star aperture. So this is the one that you're actually measuring. So we come over here and we click on the target. It says searching for comparison stars and comes up with, several other options. If you don't get a comparison star or you decide to enter comparison stars yourself, these won't show up. And you can just go ahead and select your own comparison stars by add reference star C2 or delete aperture. So you can go ahead and click on another star, and then it'll add that star as a comparison star. And so I need to explain comparison stars, I know, but let's get this going because it'll be exciting, hopefully. I'm going to right click, and then whole bunches of windows show up. Some of them are showing up on my other screen, in fact. And then it just goes through and just almost like magic makes this light curve.
Now, JD, with all those windows that opened, which windows should they pay attention to most?
I personally, I would pay attention to the plot of measurements and also the image display over here, because it'll play these like a movie. It's while the transit is being produced, it's more for entertainment value, in my opinion. But hey, that's kind of cool. Now, this is not the target I was looking at last night, or something as weird as happening, but that's good enough. We got a light curve, and then I'll go back and figure out what's going wrong or going right with this. Okay. So one thing I do want to one impression I do want to leave you with is if you have to redo it 4, 5, 6 times, don't feel bad. I sometimes have that happen. It doesn't always go right the first time. We don't write about the times that it didn't work in the paper. We only talk about the times where we got everything working right. So be prepared that sometimes that happens. And let's see here. We actually said that this was not WASP 163. We said this was TOI, TOI, right here. So I'm going to go in here and I'm going to change the name of that graph because that bothers me. There we go. Okay, and that'll change the name of the graph here. And you can save this as a PDF or PNG file. Okay, but I'm also going to show you how to make your own graph. So what you are looking for to make your own graph, you're looking for something, a really small window that looks like this. And it always seems to hide it. So you look down in your toolbar at the bottom and see if you can find that. And then you maximize that. This is all of the measurements that the program did on these images. Okay. And we want to save this. So we're going to File, Save As, and we want to save it as a table, as you know, just as we don't want to save it as a fits, but rather a .csv table. And then this was, I'm going to call this table so that we know which one it is, okay? All right, so we close that. We've already got this wonderful graph, so hopefully this is exciting. Everyone doing okay?
I don't have any questions in the chat yet, so yeah,
Okay.
Paul's right here. Karubal, are there any questions there? Or Ribera, Kina, Besa, Elias, any questions? If so, you can put them in the chat, and I will make sure to share them with JD. If there are none right now, we can continue.
I have some question. I think, can you hear me? Yeah, I think.
Yes.
So in the aperture, like when you measure, like, so the Astro AMG, it's automatically give you all the magnitude, right? I think that's how the software is working.
It's not actually giving me apparent magnitudes because we didn't give it apparent magnitudes to compare to. We actually can do that if you'd like in just a moment. And that's probably actually a good thing that we could discuss. In fact, let's just go ahead and do that.
All right, sounds good.
Okay, so I'm going to close everything except our images. So it's like we're gonna start over. Okay, so the first thing we need to do is we need to know how bright one of the stars is in this image. What we're going to be looking at is the software is actually comparing the brightnesses of two stars. And if it doesn't know how bright any of the stars are, then it just says, well, this star is, 50% as bright as this star. And it'll give you those numbers. And the reason is because, well, stars twinkle, and that's an effect of the light passing through the air. And so the blobs of warm and cold air act like lenses, and so you get a little bit more light or a little bit less light into the pupil of the telescope, and that's what causes twinkling. And so by looking at two stars that are looking through that same blob of light, you'll get a little bit more light on both of the stars, and you can say, oh well, so when you divide it out, it kind of cancels. You get 1% more light on this star, 1% more light on that star. So if you divide the two, it cancels out. Okay. And so that's what it's doing. But if we want to do apparent photometry, let's see here. let's see. Okay, we can use this star right here. We have a magnitude in V, but we really want a magnitude in R. So right here, this star. So we need to find that star. If we can find that star, then we can measure the apparent magnitude because these are in R band. They're actually a different R band, but we're going to pretend. Actually, no, we're not. We're going to get the right R band. So I know that these are probably measured in this R band. Okay. So we get the magnitude of a star that we know, that we can find. That's this one right here. Everyone help me remember where this star right here. Okay. And so we're going to go back and double check and make sure we have that star. So I think it's that star there. Does everyone agree?
It looks like it to me. What do you all think?
Okay.
Yes?
Do we have a thumbs up at least?
Yes. All right. Thank you.
Okay.
I think, yeah.
All right. Thank you. Okay. So we're going to go ahead and do aperture photometry again. And you would go ahead and measure the apertures like we did the first time, but we've already got those numbers still in here. It remembers the last set that you used. In this case, we don't want to use auto comparison stars, and I'll explain why. And Jamaica's nodding her head. We've gone through this a few times. We want it to prompt to enter reference star so that we get apparent magnitudes. So I'm going to click on that. Okay, and then we go ahead and we place apertures. So left click on the target aperture or on the target. I can zoom in with my mouse wheel, make it easier. It will kind of center on the target. So if you're not perfectly on top of it, it'll kind of click in. And then down here, is that our comparison star?
The very bottom.
I think it's right here.
Oh, did you 1, 2, 3? Oh, yeah, you're right.
Yes. Okay. Yeah. And I'm going to zoom in a little bit. Yeah. So there's this star, these two friends here, and this one down here. Okay. And then it asks me to enter the magnitude of that star. How bright what's the apparent magnitude? Gesundheit. Okay, so computer viruses. Okay, so I want to enter the magnitude of that star. I thought I had copied that. And so this is our star. Here's our comparison star. The R band magnitude 11.779. Okay, so we type that in there. And for every comparison star we click on, it will ask us to give it the magnitude. That's why I said don't do comparison stars, because we don't really want to go through all of that in this 1 hour session. Okay. You might want to do that when you're really doing the data to be careful, but I don't think we want to do it this time. You can ask it to open Simbad to look for that star. In fact, let's go ahead and just do that. We're going to click on OK. And okay, apparently you have to do that beforehand. Pardon me. And then it'll open up Simbad to that target. I don't have any other stars that I know the magnitude, so I'm just going to go ahead and right click. And then again, all these windows open up. We want to watch the light curve and the images. If you're watching the images, you can make sure that the apertures keep showing up on the stars. And watching the light curve, you can also kind of check to make sure that, things are making sense. There we go. Well, that's a lot better than last time. We might have had a star that was a poor reference star. Okay. Well, there you go. And so I'm going to go ahead and save this. I like this one. Um,
Uh, Hello, sir.
Hi.
yes.
Can you give us like 5 minutes? We trying to change the room to display the.
Oh, okay.
Just give us 5 minutes.
Okay, no problem.
Mhm. So JD, you put in the magnitude for the comparison star C2, and then it use that to give the magnitude of the target as 11.8.
Right. We'll wait until they're ready.
بزن بدأنا نستنش. Bro, can I ask you also other question in the meantime?
Yes, please do.
My name is
But we didn't quite hear your question. If it's easier to type your question in the chat, please do, and I will read it out.
Yeah. Yeah, and I'm just texting my mom, letting her know, oh, I'm online with some friends from Ethiopia.
Tell your mom hi.
Okay, I will text her. Jamika says hi.
Thank you.
Okay, Jamika says hi. There we go. Did we get the question?
No, we didn't get the question, but maybe after they finish switching rooms, can
Okay,
ask again.
sounds good. And you got my message offline, direct message?
I did. Thank
Okay.
you. Yep, that's great.
Okay.
So you were expecting a different target is what you had originally set up to show us?
Yeah, I don't know. I apparently have this like mislabeled or something.
Oh.
So this one, let's see if this is this other set of, I might have been working with this other set last night. Scale. Yeah, that's clearly a different target.
Mm-hmm, sure is.
Yeah. Okay. And so, yeah, okay, I need to change that. Actually, wait. Okay, so I've got this open in a SAO image. Okay, 4087B Bravo. Okay, good. All right, there we go.
Yeah. Okay.
That'll change, that'll solve some confusion next time.
Definitely.
Except it'll probably confuse Astronomer J, but yeah, what are you going to do?
Exactly. Yeah. This is a brilliant light curve. It's very nice.
Yeah, this is not the best one I've seen, but not a bad one. This is kind of pretty clean. I wish I had a little bit, a few more observations before and after the transit. But yeah, this is something I could post.
Oh, great.
Okay. And yeah,
Okay.
so let's see here. And there we go, 7-Eleven. Okay, that's today. Open and new. I'm going to continue practicing because if they're watching, they'll see it twice, and that's nothing wrong with that. And if they're not, then I'll still know what I'm doing and do it right the next time.
We appreciate you, JD. And this whole thing is
Yeah.
being, of course, recorded, so they'll be able to follow and listen to you as you're talking through, going back and correcting things from before, which is great.
Yeah. As I kibitz. Okay. Good. Okay. Did we ever get the question or no?
No, we didn't get the question, so I'll just wait until
Okay.
comes back after they set up
Hmm.
a new room and see if he has the question.
Okay.
Okay. Okay.
Ah,
Oh, there we
We,
go.
we just okay. When we changed the room, we got a bit problem with the internet. We try to fix it. So my question was, I only know about the IRAF reduction.
Hmm.
What I want to ask is of the astro image processing. I want to know what is the difference of those. And the other thing is when you have your own observation, is it possible
Hmm.
to data reduced in astro imaging?
What was the second part of the question?
The second part is like if I get the raw data from observatory,
Yes.
can astro imaging reduce my data? Like
Oh, do the flat field bias dark subtraction?
yes, yes, yes.
Yes, you can do. I think you can do that. I would have to look at how to do that because I'm always using LCO data, but I do
Okay.
think it can do that. I'll have to look. Um, yeah, I'd have to look, be sure.
okay.
Um, and then IRAF. I used IRAF a long time ago, and I haven't used it. I'm talking like 20 years ago. Is the one time I used IRAF, and so I don't remember it very well. But IRAF does the same kind of things where it draws the circles around and adds up all the pixels inside the circle and does the two other circles for the sky subtraction. So it does do similar things. And I don't think there's a very big difference in the quality of the output, but I could be wrong. And if you find that there is, please let me know. So I think that the real answer is for the aperture photometry like this, like what we're doing, IRAF is going to be very similar. All right. Okay. How are we doing?
Are you all set up in your room now?
Okay. Well, I will go back to the practice. So this is the saved file, and this is from the first time we ran it. I'm going to copy that. I use LibreOffice. Calculator. So the LibreOffice spreadsheet.
And LibreOffice is another free program.
Right. Yeah, and professionally, you should use something like Python. But this is good because I work with a lot of kids. And so I can go ahead and show them how to do all the calculations in this. It's a little easier learning curve generally. And it gives you all the various numbers that you need, and you can go ahead and let me see here. So sky per pixel. So just looking at this. So relative flux T1, that's like the entire reduced. That should be the entire reduced thing. So if I copy that column over here and I copy the Julian date over here, I should just be able to make a graph of that. There we go. Yeah, and that's what we got the first time.
Mm-hmm.
Okay, we can go ahead and put our elements in here. This is TOI 4087. X-axis is, and y-axis is, okay, so we get there. And then the other thing we can look at is the way it did this is it looks at the let's see. So there's the relative flux. Come over here, we can get the relative flux error. So it gives you error estimates, which is always good. And then you can go further. And then it starts talking about source minus sky. This would be counts. And so this would be uncorrected for the twinkling. So this would not include dividing by the other star. So I'm going to guess that this is going to come out pretty rough if I graph this. Yeah, see, there we go. Yeah, that's not a bad idea to show that. So this is just how bright the star is in each image. And then this is how bright the star is in each image divided by the brightness of the other stars. So so it removes a lot of that twinkling. Or if there's a little bit of some light cloud cover, maybe you lose, 5% of the light. So you're 0.95 times as bright as you should be. Well, the comparison stars are also going to be 0.95 times as bright as they should be without that cloud. And so then you divide 0.95 times your target times 0.95 times your comparison stars. 0.95s drop out. And maybe I should be writing that, but oh well. Okay, yell if you want me to cover anything. How are we doing?
Do you have questions? Ooh, that's a lot of data there.
Yeah, a lot of data. And this one, we should see somewhere along here something where it says source apparent magnitudes. Okay, C2 is the comparison star. So these are always going to be 11.779. But then if we come over here to over here, there should be something like that. Okay, this will be the magnitude of the target, the apparent magnitude of the target. So what it's done is it's compared that the brightness, how bright the comparison star looks to how bright the target looks, and then it can tell how bright the target really is.
Right. Which
Okay.
I believe was one of Karubo's questions. Can we get
Right.
right? That's great.
Yeah.
Should we
That's
do
why we went back and did it again.
right? Exactly.
Yeah.
Karubo, would you like us to go? Would you like JD to go back through this with maybe another star?
Sure. I guess we can try to use another star. Yes. Okay. Yeah.
Yes.
Everyone, are we all back?
Yes. Yeah, we're back. Yes, we're back. We have been
Oh.
you.
Okay, great. Okay, so where do you want me to start from? I don't know how. Okay.
Like what columns are.
Pardon?
Can you a little bit explain about the table that you like the H
Okay.
magnitude, the false half max?
Right. Okay. So I'm going to save this with a little different name so that we can look at both of them, because I think that there's definitely something to be learned from both of them. Okay, there's magnitude. Okay. What I do to get this into a spreadsheet is I open this up with a text notepad. Are you working with PCs or Macs?
We're working with
PCs?
Yes,
Okay,
yes.
okay, then that'll make it easier to follow what I'm doing, I think. Okay, great. Okay. Oh, we're getting a little echo. I'll try not to speak too loud. So I open this with Notepad. So I just right click on this. It says open with, go to Notepad. And then I can copy this. And like I said, LibreOffice, I like this partly because it's free. And I like things that are free. But it also works very well. So, all right. So we've got all these columns. First one, the label, that's just the file name. Okay. Slice, that's a number that it gave to each image. Whether or not it's saturated. And then this is the Julian date minus, what is it, 240 million or something like that? 2.4 million. Okay. That's just to make the number a little smaller. This is the Julian date. Not really sure that to worry about that. This is the air mass. This is how much air we're looking through. So straight up is 1, and about 30 degrees would be 2 times. Think about sitting at the bottom of a swimming pool. When you look straight up, you're looking through the least amount of water to get out of the swimming pool. It's the same with our atmosphere. It's like it's a plane parallel model, except for they've got a little better calculation. But you look through less air when you look straight up. This is the full width half max. This is how much the light has been spread out in measurements of the sky. Source radius, that's our inner circle that we set. Sky inner radius is the second circle that we set, and that's the third circle we set. Okay, relative flux T1. What this is this is the brightness of that target divided by the brightness of the comparison star. Okay, so if I copy this, whoop, not what I wanted to do. Where do we go? Relative flux T1. Okay. So if I copy this over here, and then I get the Julian date. Okay, you're familiar with Julian date, I assume? Just the number of days since a specific point. So it's just time in days. And so if I make a graph with this, it should look pretty good. Not bad.
Sorry to interject, but if you can,
No, please do interrupt.
if you can maximize the speed so that it will be visible.
I'm having a hard time hearing you. Could you
If you
type in the... Go ahead.
If you can make your window full screen.
Did you ask to make it a full screen?
Yes.
Full screen, yes, okay.
There, is that better?
Yeah. Better.
Okay. Yeah, okay. Sorry about that. Thanks for letting me know. Okay, so yeah, we've copied the Julian date, relative flux, and let's zoom in even a bit more. Let's just make it easy. Then I can take off my glasses. There, that's much better. Okay, so we've just basically plotted the relative flux versus the Julian date, and that gives us a nice light curve, kind of what we would expect. So that's what relative flux is. It's the brightness of the target divided by the brightness of the comparison star as measured from the image. So how bright they both appear in the image. Okay. Relative flux error is, just the error of this relative flux. Signal to noise. You got a lot of little things. Total counts is the total counts inside the middle circle. And then you have other little measurements here that I wouldn't worry too much about unless you really want to get into it. It gives you the measurement, right ascension, declination, apparently. This is a little more interesting. This is your source counts. This is how many counts that you're actually getting from your center aperture after you subtract off the sky brightness. So it's source minus sky. So if we copy this, and make another graph over here. And we'll also want this, which is our Julian date. So if I make a graph of this, it's not going to look very good. You'll probably be able to see, yeah, there's probably a transit in there, but as you're looking through more atmosphere, you're losing light. And so you get this trend over in this that makes it very difficult to see. So I'm going to delete this. And then if I go a little further to comparison 2, source minus sky for comparison 2, if I grab that, and then I divide the one by the other, okay? So all I've done is in each one of these cells, I've divided this divided by that. And then when you copy and paste into the cells, it'll fix the formula. I'm going to go ahead, insert a column before, and stop me if I'm doing too many spreadsheet gymnastics. Okay, so here's our Julian date column, and this is the source minus the comparison star. If we do a graph of those, it should look pretty nice again. Okay.
Yeah, you can clearly see the transit there.
Yeah, you can. It's much better, and so that's a really good demonstration of why you want to do comparison photometry, relative photometry. The other thing that that this set has, we remember how we did the magnitude of the check star. So if we come over here, source apparent magnitude, and this is for the comparison star. C2 is your comparison. Notice it says, okay, it's 11.79 all the way down. Okay. So basically it just said, oh, you told me what this is. This is how bright this star really is. So and then it goes through and calculates based on how bright that star is, how bright is the target star. Source apparent magnitude T1. So this is magnitude of the target star. So I'm going to put that in this column. I'm going to grab that here. And we're going to make a graph of that. All right. And so I'm just going to do an XY scatter plot, which is what I've been doing. And since it's magnitude, it's brighter is down. So I can go ahead and reverse direction so it doesn't creep me out. Okay, is this making sense? Am I being helpful?
Yes, Karuba, let us know if this is useful.
Mm-hmm.
Oh, let me see. Or you can type in the chat.
Yeah.
So, okay. While we're waiting for that response there, is
Okay.
there, can we look at did you have some variable star data that we could look at quickly?
Possibly. Let's see here. Let's take a look in the. Let's see if there's something that might be interesting. Variable stars. A.D. Leonos. I think that's an R.R. Lare.
Yeah, I think when we had our meeting, we you looked at this RR Lyrae star.
Yeah, I think that was the Hercules one in Hercules.
It was Hercules, yep.
Yeah, so that would be one of these. But I'm hoping this. Let me see what A.D. Leonis is. So, of course, when I'm trying to figure out what something is, we go back to Sinbad. Sinbad's our friend. It's a high proper motion star. Huh. Wonder why it's in variable stars. Oh, it is a variable star. Okay, well, let's ask AAVSO.
I think
Can you now? Yes, can you hear me?
yes, we can hear you
Yes.
now.
Oh yeah, we've been following along. We just had a little bit of an issue with the audio input. The graph, the plot earlier was helpful. I think it showed the the trace well. So yeah, we've been trying to answer some of their questions from our side as well. That's why we've been a bit quiet, but we are
Oh,
following along.
okay. All right. Is it going? Do you have any questions, or should we?
I think I should open it to the house. If you have any questions so far on the things we've
Yes.
talked about,
And please,
ask
don't feel
questions.
intimidated.
I mean, we have an astronomer here as well, and also you can ask JD. So whichever one is convenient for you to ask, you can raise your questions. Don't be shy.
Yes.
Okay, I guess everybody's in unison nodding along, so they do understand what's going on so far, I guess.
Okay. All right. Well, do we want to go through another example of making a graph, or do we want to possibly look at something else?
What do you guys think?
I think I can prefer like if you give them like some objects, like they can also go to LCO. They can then do the like the observation and the data reduction, how it will be. If you can do that, that's much helpful.
You should be able to download. Okay, so just for a practice session, you should be able to download some of these exoplanet observations. Let me find a good one. I'll find a good one at another time. Oh, there we go. Okay, no, that's not a good one. But I can find a good set for you. This one was, I think, a good one. Yeah, okay, that's a good set. So I'll see if I can find the link to that data set. You should be able to download that from Las Cumbres. It's not the variable stars you're looking for, but it should be something you can practice with at least. And then let's go back and look real quick, because I'm trying to remember what this AD Leonis is, because that might be something that we could look at that would be interested in. Oh, I bet I know what that is. Oh, I know what that is. Yeah, that was for Chi. That's not going to be too interesting, but we could go into an RR Lare, um, but I've already done that. And so what I think that maybe we want to do, um, have you discussed phasing of data? Doing a phase plot?
No.
No. Do you know what a phase plot is?
I don't think they, I think you can explain about the phase plot also, how to detect the period also. I think that's also interesting.
How to detect what? Pardon?
Also the period, how to detect the period.
Oh, the period.
Yes, the period. Oh, yes, yes. Right. So, okay. When we're looking at observing these variable stars, let's say it has a nice regular period like this, pretending that that's a nice sine wave, even though it's poorly drawn. Okay. And we might get observations here, then here, then here, then here, then here, then here, here, maybe one here, maybe another here. And from that, it's going to look, almost kind of like noise. So what we can do, let's pretend that we know what the period is. And the period is sort of the distance, the time between two peaks. So I should label my graphs, shouldn't I? This is time in this direction, and this is flux or brightness in this direction. Okay, so the star we're pretending goes up and down kind of sinusoidally. This might be an AW star. It's a contact binary star. And so the period is from this peak to this peak. Actually, if it were an AW star, you'd want to go through two peaks, but details for later. Okay. So that from mathematical point of view, this is the period. And so for an RR Lare, we'll go with an RR Lare. This is what the period is. And if we pretend that we know what the period is, then we can break here and here and then shift this whole thing by one period in this direction. Okay, so then I get to add this point in here. Okay, we're going to do the same thing here. So we're going to shift these 3 points, 2 periods back. We get this. We get this. And we get this right here. Okay, and then we do the next two, or the next section. And eventually, as you get more and more sections, that way you can fill in the full period. And you can see what the light curve looks like. All right. But the challenge, the biggest part of this challenge is figuring out what the period is. And there are a lot of techniques to do that, but there is a piece of software which was made by the American Association of Variable Star Observers, AAVSO. Again, free. You'll find a theme that I like free. And what you need to do to make this is you have a text document which has the time and the flux or magnitude, just those two columns. And so you can make that by going in. Once you've got it here, you could grab these two, copy that, and paste it in here. But I'm not going to do that. I'm going to change this because this is an RR Lyrae star. And I'll show you where I got this data because I think it'll be really cool. But let's look at V star real quick. So these are from the Atlas data, from the Assassin Observatory. You can go and grab these measurements. They already have magnitudes for you. And then you just grab the Julian date and the magnitude, paste it in here. I'm going to go ahead and open this file. So in VStar, this is what you get when you open it. We click on File, New Star from File. Okay. And then you navigate to where that is. Excuse me as we go through the back corners of my computer here. Okay. This is V1283 Hercules, which is an RR Lyrae. These are pulsating variable stars. It's kind of fun. And this is the data we get. This is a plot of the magnitude versus time. Okay. And it looks like a mess. So what we want to do is let's search for the frequency. So under analysis, we can do DC, DFT. So this is like similar to a Fourier transform search with a frequency range. Okay. And I'm going to select OK. Now the frequency is in units of per day, how many per day. And I know that the RR Lyrae stars, sometimes you'll get about 1 to 5 per day. Between 1 and 5 cycles per day. So I'm going to give that for the low and high frequency range. And then the resolution, I'm going to leave that, but you can alter that to do higher or lower resolution, depending on computing time and what you need. And I'm going to tell it, okay. Thanks for a minute. Then it comes up with this analysis chart. The spikes means there's a lot of power in those. In other words, these are the places where there's a good match. We can come over to top hits. Okay. The top hit is a period of 0.27. And so we're going to do a phase plot. That's the phase. It's going to go ahead and do what I was showing you here. It's going to do that with this data. Only this data goes out to probably hundreds of periods. Okay. So we're going to do a new phase plot, and drum roll, this is what looks like magic to me. So it checks that I want this period and this epoch. This is the starting point for the plot. And that's what it looks like after it's been ordered. To me, it always looks like magic. Does it look like magic to you?
It's pretty magical.
Okay. So then you now know what the period is. You can again save this plot or write in your notebook, here's the period. So that's a really good way to look for periods. Now, if you're looking for periods and it's something like an RR Lare in particular, pulsating variables, something that has something nice, a nice smooth curve, one place you can go for data is the Assassin project. And if you go to the Sky Patrol Photometry database, I don't think you need to log in to this, but I could be wrong. This is where I got the data that I'm working with here. But if you were to find something really cool in this database and go ahead and publish it and credit them, they would be like, that's great. They would love it if you would do that. So don't feel like you're stealing someone's data. Feel like they've put this data out there for you to use. As long as you give them credit for providing the data for you, they would love for you to do some great science with their observations. So this is the right ascension and declination of this variable star, of this RR Lare star. And sometimes it doesn't let you copy and paste those. Necessary, you just type it in. So you're going to search for sources. Here's the right ascension. And I just type in the declination. And I've already done that. So there we go. This is a search radius, 7 arc seconds, 7.8 arc seconds. That's fine. I don't know why it's choosing that, but I don't need a very large search radius because I already know the coordinates. I looked these up on Simbad at some point, and then I can go ahead and search. Oh, here's the target. I can click on that, and it'll come up with this wonderful table. Okay, so here's the Julian date. The flux, I think that's probably the real flux, but obviously it was not detected in these images. Tells you the filter here. The quality, which is strange that it says it's good quality on this one when it didn't get any flux, so I don't know what the story is. But we can download this as a CSV table. Click on that. And then once I get the download complete, I can click on that, open it in LibreOffice, and then I can go through. Now, there are different filters. They have a V filter and a G filter. Those will not always compare very well. So we want to just look at the G filters because I think there are more. So I'm going to go ahead and sort these. Data, sort by filter. Okay. Then I can go down to the bottom of my G filters. Okay, so the G filter is a green filter. The V is what's called a visual filter, which is also green, but for historic reasons, it matches basically the brightnesses we see by eye most closely. So they call it a visual filter. So we insert a row above. We get our G filters. So we've just got our G filters and we know where that ends. I just like putting a space in here so that I don't lose data. And let's create a new page in our spreadsheet. Grab the Julian date, paste here. grab the G-band filter, or not the G-band filter. I tried that before and it basically told me I was being silly. So magnitude, that's what we want. Put the magnitude there. Okay. If we want, we can then sort this by magnitude. We don't need to. Or sort this by, not magnitude, by Julian date, sort of by time. So we get the first. Then I just copy this. And I paste that into a text document. So, oh my, if I open that, I bet you know what you're going to find, but let's make a new document here. Open this up, paste that in here, save that. And let's go ahead and open this new one in this. So new star from file. So we just made this one. Okay. Anyone remember what we do? We do analysis, frequency range. Okay. Knowing that the frequency is going to be between 1 per day and 4 per day, I'm going to go ahead and put those numbers in. Click on OK. And here we go. Maybe I was doing something different last time. Top hits. I'm going to click on this top hit, make a new phase plot. It automatically puts the period in. The epoch is just sort of like the start where time equals 0. Go ahead and click on that, and there it is.
Wow, it looks great.
Yeah, to me that always it's like magic to me. That's one of the fun things with variable stars. One of the really fun things is to see that happen.
Okay, so let's pause here. Are there questions? Karuba, was this, I know one of the questions was how to find the period, which JD went through, which is brilliant. Questions at all about this plot showing the phase? Hopefully they aren't having any issues there with the,
Yeah.
okay. So,
Oh, good. You've got the links there. Thank you for doing that.
oh yeah, absolutely. And
Yes, that's great.
I will send all these links to everyone who's in the session right now so that they have them. And
Yeah.
so Kruba, what I'm hoping is that when you all get your data, or even if you have it now, if you'd like, JD, would you potentially be open to working with some of their data to show them how to do the processing with their actual?
Yeah, I would be more than happy to. But hopefully what we'll be able to do is have them work with the data with me sitting in the background saying, do this, do this. Oh, why don't you try this? Because that, there's the Hawaiian saying, makahana ka'ike, the knowledge is in the doing. And
Yep,
so
that's how
if
I
we can
learned.
get if we can get that worked out, because I know that there's a little bit of communications challenge going halfway around the world, not a surprise.
Right.
But yeah, if we can do that, that'd be a lot of fun. I really enjoy that.
Yeah.
And yeah,
That will be perfect. Sorry, but we dropped just for a few seconds on the last phase of the data processing part. Right after you load the data and the plot showed up. Besides that, I
okay.
think if they have any questions, they can definitely ask.
Okay. Yes, please, if there are any questions, feel free.
So I think the question I want to ask you is like, so they will organize their data in text format, like having the HJD and the magnitude, and
Right.
so they will try to upload it in. I think it's a software that will plot the light curve, VStar.
Yeah, yeah, V star will plot the light curve. So let's go ahead and do that real quick. So yeah, once you have this table, and there are other ways to do this. This is just my way of doing it. Okay. And so you have this table here, and then V star, it will it'll plot the data. It'll do a light curve. So that's the brightness or magnitude in this case versus time from this table here. Okay.
Okay. So what else? Okay. Continue, Lens.
Okay. So at that point, what we want to do is we want to try to find the frequency. That was the question. So we're going to do under analysis, there is this the scan with frequency range. Let's try that. I know that this is an RR Lyrae star, and that the frequency of an RR Lyrae star is sort of 1 to maybe about 5 per day. And these are in units of per day. And then the resolution, I'm going to leave it pretty small. You can make it bigger or smaller as needed. Feel free to play around with that. Then we just click on OK. Pardon me. So then it thinks, and these spikes are where there's a lot of power. That's like when you're tuning the radio and you hit the radio station, it gets louder. That's kind of what's happening. This is basically it's doing a Fourier transform. And so you can go ahead and click on that and take a look at it. But best thing to do is maybe come over to top hits. That gives us the periods that have the most power in them. In other words, the biggest spikes. And so here's this. And we can create a new phase plot. It'll automatically put the selected one in for the period. This is the 0 point. Don't worry about that. That's just where time equals 0. It'll shift things around, but it really won't change much. And then suddenly, now it's rearranged those same observations. It's done the phasing, that shifting by integer periods, so that it only goes through one cycle. And then so this is one period here, and then it repeats on the right hand, just to give a little bit clearer picture for us to look at. Is that what you needed?
Yes, yes.
And one other thing we could do is we could create a model, which basically just would be a sine wave. Okay, so harmonics per period. Okay, so this is so just one harmonic. This will be like a sine wave plotted on top of that. So it's a pretty nice match. RR Lyraes are pretty sinusoidal in their variability.
That's good.
All right. Does that help?
Yes, yes, yes.
Okay, good. Good.
Do you have any other questions?
And I know we went through a lot tonight or today. So don't feel bad if you've got questions. Please feel free to ask them. Also, please, feel free to ask me to come back and even if I have to start from the very beginning again, no problem. It's a lot to learn in a very short time.
Okay, we have one question, I think.
Oh yes, good. Okay.
Where do you get the table of the Julian dates and the magnitude? That's
Where do we get the Julian dates and the magnitudes?
how
Okay.
is that?
Well, the two places. One, you can measure these magnitudes and Julian dates in the observations you take. And another place is this Assassin Sky Patrol database. That's where I got obtained the observations that we're looking at here. That we're looking at here somewhere. Yes, here. Does that help? And if I don't answer the question, just keep pushing me to answer until you understand.
I think we will share the website where you guys will be able the observational data you need. That's the place where you download all the data, either from your LCO observation or from the website provided. Am I right?
Yes. So you either you can download observations from somewhere like Assassin, which will give you the magnitudes and the Julian dates, or from your own observations, including Las Cumbres, that you've measured the brightness, the relative flux, or the apparent magnitudes, and put and you can use those in this V-STAR program as well.
The other question I want to ask you is, for example, how many data it's needed to light curve, like to get the light curve in the period, like how many days or the years they want to know?
How many? So how many periods of observations do you need to get the period? How many cycles? It depends. I mean, if you start talking to a mathematician, they might tell you, oh, you need about two samples, 2 or 3 samples. If you know the type of variable star, and it's something like like this, you might be able to just kind of sample at the 2 extrema. So at the minimum and the maximum. What? Oh no, I just killed my table. Okay, there we go. Okay. So you might be able to just kind of look for the peak. And then if you have a good idea of the frequency, you might be able to go observe it at the next peak and then kind of fit the two together. And I've actually done that in some cases. If you want to actually do it in this method, I would say get several observations over at least a full period, but probably 2 or 3 periods. It's a tricky question, to be honest, of how much you really need.
Okay. Also, if you can like show them like how B minus V magnitude plots are. Can we do that or?
Oh, B minus V plots? Yes, yes. Let me see if I've got some observations. Yeah, so color magnitude. So a color magnitude diagram, correct? Or color magnitude diagram. Is that
Yes.
correct?
Yes.
Yeah, let me see what I've got. Where would I have some hot star satellites, quasar? Hmm. Oh, okay. Let's get some data from Las Cumbres. This will be a different piece of software. Um, so Omega Centauri. Let's get data on Omega Centauri. Okay, so it's a nice globular cluster. Um, and I'm going to grab the reduced data. And do I have? Okay, I don't have this program on my current computer. It's been a while since I've used it. Aperture photometry tool is what I might suggest. Again, sticking with free software because we are all on budgets. This was produced by a guy at NASA JPL, and it is free. Um, and so hopefully I can get this up and working real quick. Okay, there's our data. Is it blocking us? Shoots, it might be blocking it.
I'm attempting to download it.
Yeah, it might be blocking my download. Um,
I'm having trouble with it also.
okay. Yeah. Huh. That's too bad because that's a good.
Maybe Python, if you have like a Python package something.
Yeah, to be honest, yeah. So Python. Yeah, I don't have a good know of a good Python tool. I wonder if yeah, I would have to sort out how to do that, to be honest. Because the idea is that you want to do what you want to do is you want to do um, aperture photometry on 1,000 sources in your image, and you have 3 images that you want to basically have the same do the photometry on the same sources in all 3 images, and then you can plot the blue the B minus V for that. So let me I know somebody I can talk to at Caltech and ask about APT, see what's happening with it.